The JWST stands tall as the most powerful and sophisticated observatory ever built to study space. It embarked on its outer space journey in December 2021 and gracefully settled into its final orbit around the Sun-Earth Lagrange point 2 in January 2022. Since then, it has been sending us breathtaking images of the ancient and distant cosmos, unveiling new mysteries about the origins of stars, galaxies, and planets. However, some of these captivating images have left scientists puzzled, challenging their current understanding of the vast universe and the principles of the Big Bang Theory. The Big Bang Theory is widely accepted as the explanation for the beginning and evolution of the cosmos. It suggests that the universe emerged approximately 14 billion years ago, from a boiling and dense state, expanding and cooling over time. Around 200 million years after the colossal explosion, the first stars and galaxies formed, gradually enriching interstellar space with heavier elements through nuclear fusion and supernova explosions. But now, some of the images received from the JWST have raised perplexing questions, casting doubt on the reliability of the Big Bang Theory. If this theory, which has been widely accepted for many decades, is suddenly disproven, where will the entire field of science go from there? What other beliefs are contradicting? The growing concern among astronomers about this recent development is unsettling. The validity of the Big Bang Theory depends heavily on the idea of inflation, which proposes that the universe experienced a rapid expansion of immense magnitude, surpassing the speed of light. However, scientific endeavors have failed to provide solid evidence supporting cosmic inflation, leaving the theory plagued with profound mysteries since its inception. Interestingly, even Paul Steinhardt, one of the architects of the theory, has now criticized it as misguided and lacking scientific significance. Are we now compelled to abandon the theory of cosmic inflation and explore alternative ideas? Could alternative hypotheses like the Big Bounce, or disregarding the speed of light as a constant, offer a resolution? Or are these alternatives just temporary solutions to avoid the more radical conclusion that it may be time to let go of the entire concept of the Big Bang? For example, in June 2023, astronomers using the JWST made a remarkable discovery of the farthest smoke molecules ever observed in the cosmic expanse. These molecules, known as Polycyclic Aromatic hydrocarbons or PAHs, usually appear near young, massive stars emitting abundant ultraviolet light. The puzzle arises from the detection of these molecules in a galaxy located 12.3 billion light-years away, meaning we see it as having existed only 1.5 billion years after the universe's evolution. This discovery contradicts expectations because, according to the conventional Big Bang Theory, the universe began 13.8 billion years ago, in an intensely hot and dense state, gradually expanding and cooling. As I've said before, the interstellar medium became gradually enriched with heavier elements through nuclear fusion and supernova explosions. Since PAHs are complex organic molecules relying on carbon and hydrogen atoms, their significant abundance during the early stages of cosmic history seems contradictory and unlikely. The remarkable discovery made by scientists raises intriguing questions about our understanding of the universe and its origins. Either the galaxy SPT 0418-47 has exhibited an exceptional ability to produce stars and polycyclic aromatic hydrocarbons, PAHs, or our current knowledge of the Big Bang and the early cosmos is either incomplete or flawed. Alternative theories such as inflationary cosmology, cyclic cosmology, or quantum gravity have been proposed to explain this anomaly. These theories challenge the conventional idea that the Big Bang was a singular event that marked the beginning of time and space. Another interesting example of how the JWST has revolutionized our perspective on the universe and the Big Bang Theory is the discovery of numerous massive galaxies in the early cosmos. Astronomers using the JWST announced in January 2023 that they had found 6 potential massive galaxies, observed around 500 to 800 million years after the Big Bang. These galaxies are estimated to have masses ranging from 100 billion to 300 billion times that of our Sun, comparable to some of the massive galaxies in the present-day universe. This finding is extraordinary because, according to the standard model of galaxy formation, it should take much longer for massive galaxies to form and grow compared to smaller ones. The existence of such massive galaxies shortly after the Big Bang suggests that they must have formed rapidly and efficiently, possibly through the merging of smaller galaxies or intense periods of star formation. This challenges certain assumptions and predictions made by existing models of galaxy formation and evolution. Now let's delve into the nature of time itself. Is time an inherent aspect of reality, or merely a construct of our consciousness? Time represents one of the most fundamental and mysterious concepts in science and philosophy. We commonly perceive time as a continuous sequence of events, extending from the past, through the present, and into the future. Furthermore, we consider time to be an absolute and objective entity that exists independently of our perception and measurement. However, various theories and experiments have cast doubt on these intuitive notions, revealing the illusory nature of time. Einstein's theory of relativity is one such theory that challenges our intuitive understanding of time. According to this theory, time is not absolute, but rather depends on the observer's motion and position within a gravitational field. Einstein's theory suggests that time can stretch or contract based on an observer's velocity or the intensity of the gravitational field they are in. For instance, an astronaut approaching a black hole would experience time slowing down to the point of stopping as they neared the event horizon, while an observer from afar would see them suspended in an eternal moment. However, relativity is not the only theory that disrupts our conventional view of time. Quantum mechanics, the theory that explains the behavior of subatomic particles, also challenges our understanding of time. It indicates that time lacks determinism and instead has a probabilistic nature, meaning that we can't predict the outcome of an event with certainty, but only with a certain probability. Quantum entanglement is an example of this phenomenon, where two particles can share a quantum state despite being separated by vast distances. Measuring a property of one particle, such as its spin or polarization, instantaneously provides knowledge on the corresponding property of the other particle. This seemingly defies the concept of causality and implies the possibility of faster-than-light communication. However, within the framework of quantum mechanics, such occurrences are considered entirely possible due to the absence of an objective order of events in nature. Another aspect of time that challenges our understanding of time is quantum superposition. For example, it's a phenomenon where a particle can exist in multiple states simultaneously until an observation forces it into a definite form. Think of Schrödinger's famous cat experiment, where a cat was locked inside a box. Inside the box, there is a radioactive source and a poison device that will be triggered if an atom decays. According to quantum mechanics, until someone opens the box and looks at the cat, it exists in a strange state where it's both alive and dead at the same time. And this makes us wonder, does our observation create the reality of the cat's condition, or does it simply reveal what was already there? Some physicists propose that time might not be a functional element of reality, but rather an emergent concept that arises from more basic constituents. Carlo Rovelli, a renowned theoretical physicist, suggests that time is just a construct, created by our limited perspective and memory. He believes that true reality transcends time and remains eternal, while our perception of time serves as a measure of disorder or entropy within a system. This idea aligns with the block universe theory, which stems from the principles of relativity. According to this theory, the past, present, and future all coexist in a four-dimensional space-time framework. There is no objective flow of time. Instead, the experience of changing and progression depends on the observer's position. This means that free will and causality might be illusory, since all events, past and future, are already predetermined within this block. But if time is an illusion and everything is predetermined, how do we explain the apparent forward motion of time and the arrow of time? Why do we remember the past, but not the future? Why do things break, but not spontaneously fix themselves? Why do we age, but not reverse the process? These questions have puzzled philosophers and scientists for centuries, and we still don't have definitive answers. One possible explanation involves the second law of thermodynamics, which states that the entropy or disorder of a closed system always increases or remains the same over time. Natural processes tend to move from order to chaos, establishing an irreversible temporal trajectory. For example, breaking an egg increases its entropy, since it becomes mixed and exposed to its surroundings. Restoring the egg to its original state would require an enormous amount of energy and information. Similarly, as we age, our bodies accumulate damage and lose regenerative abilities. Increasing their entropy and reversing this process would require miraculous intervention. However, not everyone agrees with this explanation. Some critics argue that the second law of thermodynamics is a statistical principle that applies to large numbers of particles, not individual events. They also question whether entropy is an intrinsic property or depends on how we define and measure it. Moreover, they raise intriguing concerns about why the universe began with exceptionally low entropy and has consistently increased over time. These profound questions remain unresolved mysteries in the fields of cosmology and physics. Time shapes our existence while simultaneously challenging our understanding, as it is both a construct of our minds and a genuine aspect of reality. It defines our humanity but also limits our comprehension. As Albert Einstein wisely remarked, the distinction between past, present, and future is but a stubbornly persistent illusion. And that brings us to the end of this video. Do you think time is real, or is it just a figment of your imagination? Let us know in the comments section. And as always, keep exploring.